Hey guys, welcome back to chapter 16. In this video, I'm going to work another problem, but I'm going to give you a little bit of a wrinkle in this problem. So you already have the skill set from chapter 15 to solve this problem, but I wanted to introduce it just so you could see it applied to chapter 16. So going the other way, initially a 0.1 molar weak acid was mixed with water. Once it reached equilibrium, it had a pH measured to be 4.25. Find the Ka. So what do I mean by going the other way? Up until this point, we've been solving using Ka and then solving for pH. In this problem, I give you pH. I'm asking you to solve for Ka. If you think back to chapter 15, this is actually one of the easier problems. So in this problem, we'll have the ability to fill out the ice table entirely with numbers, and then use the numbers from that ice table to solve for Ka. So a little bit easier, but I wanted to show you how it's done. So first things first, we need to write an equation for the ionization of this acid. So weak acid, it looks like they're using a generic acid, so we're just going to call it HA. It's mixed with water. And then acids are proton donors, so we're going to have that A minus after it gives away the hydrogen. And then water is going to be our base, our proton acceptor. It's going to take on that hydrogen. So there's our generic equation for this weak acid. Next thing we'll be able to do is a Ka equation. So this is what we're ultimately going to have to fill out to solve this problem. So concentration of our products over concentration of our reactants. And again, water's not included because it's a liquid. Okay. Last thing we need to do for this is do our ice table. So here's our ice table. Let me clear off some of this stuff. Here's our ice table with our reactants and then our two products. Okay. So initially, a weak acid was at 0.1 molar. So initially, we're going to have that 0.1 molar here. And there's no mention of the other two. So we're going to put 0 and 0. So if we're trying to determine the Ka value, we need to be able to fill this table in with numbers. So what is the only piece of this problem that we have not used? And then how are we going to use that piece to fill in this table with numbers? Well, the piece that we haven't used is this guy right here. So pH is 4.25, okay? We can go from we can go from the concentration of the hydronium to pH, correct? So this is a skill that we've practiced time and time again. But how do we get from the pH to the hydronium concentration? How do we go the other way? Well, we can do it. We just have to take the inverse of the log. So what in the world is the inverse or the opposite of a negative log? So the hydronium concentration is going to be this. It's going to be 10 to the negative pH. Okay, so that's the inverse of the log. So if I want to solve for hydronium concentration, I just take 10 and raise it to the negative pH. So to get the hydronium concentration, I'm going to take 10 raised to the negative 4.25. So type that into my calculator, 10 caret negative 4.25. And I get that the hydronium concentration is 5.6 times 10 to the negative fifth. Okay. Great. We learned a new skill. We learned how to go from pH to hydronium concentration. But how does that help us? Well, if we read this closely, it says once it reached equilibrium, the pH was. So this hydronium concentration is the concentration at equilibrium. So we can take equilibrium pH, do the inverse, and we can determine that this is 5.6 times 10 to the negative fifth, which means our change is 5.6 times 10 to the negative fifth, which means we can fill out the rest of this table. All right, so change over here, remember, is going to be a negative, so it's going down by the factor of 5.6 times 10 to the negative fifth. So I'm going to take 0.1 minus 5.6 times 10 to the negative fifth. And I'm going to get 0.00, oh, no, just kidding, 0.0999. Okay. Well, now that I have an equation for Ka, now that I have all of the numbers in my table at equilibrium, now I just need to plug and chug. So Ka is concentration of our products. Gracious, I can't write. Over concentration of our reactants. So Ka is going to be 5.6 times 10 to the negative fifth times 5.6 times 10 to the negative fifth divided by equilibrium concentration of 0.0999. So Ka equals 5.6 times 10 to the negative fifth times 5.6 times 10 to the negative fifth. And that is going to be divided by 0.0999. Ka is 3.14 times 10 to the negative 8th. So if you are given pH and you are asked to determine the Ka value, just remember that this is the type of ice table that we can fill in all the way with numbers. So here's another example. So why don't you guys go ahead and pause the video, try to work through this example, and then I'll catch up to you. All right. So first equation. So formic acid. It's not one of the big five. That's how we know that it's a weak acid. It is going to dissociate in water. Formic acid, being an acid, is going to donate a proton. So we'll be left with this. And hydrogen is going to attach to water to create this. So there is our equation. Ka is going to be products over reactants. So equilibrium concentration over equilibrium concentration. Right. Now we're going to fill out our ice table. So ice table, our reactant, product. Initial concentration of our reactant is 0.1. No mention of the other two, so those are going to be 0. And then at equilibrium, there's its pH. So we need to go from pH to concentration of hydronium at equilibrium. So I'm going to take concentration of hydronium equals 10 to the negative 3.38. So 10 to the negative 3.38. And our hydroxide concentration is, I'm just going to write it right in the table, is 4.16 times 10 to the negative fourth. Okay. If I have that one, I can fill in the rest of the table. So the change must be 4.16 times 10 to the negative fourth. 4.16 times 10 to the negative fourth. 4.16 times 10 to the negative fourth. And this is going to be minus 4.16 times 10 to the negative fourth. So 0.1 minus 4.16 times 10 to the negative fourth. And down here, we're going to have 0.0996. Okay. So now we have a Ka equation. Now we've got our numbers filled in our table. We can just plug and chug our way through it. So Ka equals, this is 4.16 times 10 to the negative fourth times 4.16 times 10 to the negative fourth over 0.0996. So Ka equals negative 4 divided by 0.0996. So our Ka is 1.74 times 10 to the negative 6. I hope you guys found these two problems helpful.